In this video, I want to discuss a little further about histograms. Again, histograms are visual representations of our data. We can use histograms to visualize what our numbers would look like. For example, for your worksheet, you did bacterial counts for surface A and surface B. You then recorded the frequency of those counts in your tables on page 31. You then created a histogram to visualize that data. Now, why do we create histograms? Not only do you need to be able to create a histogram, but you also need to make inferences on what that picture or what that graph might say. We can start to uncover patterns in our data by visualizing them with graphs. For example, your graph might have looked something like this. We have surface A is the blue and surface B is the pink. Again, number of colonies on the x-axis, our frequency on the y-axis. Now, if you look at this graph, you can see a pattern in the graph. Over here towards the left side of the graph, these are our number of colonies that are lower, meaning that they have fewer amounts of bacteria. When we look at this side of the graph, we can see that surface A, our blue bars, are higher than surface B, meaning that surface A at this point in the graph actually has fewer bacteria as compared to this side of the graph. On this side of the graph, we can see that surface B, our pink bars, are higher than surface A, our blue bars. Just by looking at this, we can see that surface B has higher numbers of bacteria on this side of the graph. So visually, we can start to uncover patterns in our data. If you think back to the hypothesis that you made about your surfaces, it would look something like this. You chose a clean surface and a dirty surface. What you were really doing was making a hypothesis that surface A would have less bacteria than surface B. You are also making the hypothesis that surface A and surface B are not equal, meaning you didn't think they would have the same amounts of bacteria on them. So in this case, with our graph we created, we can say, yes, our hypothesis that surface A has less bacteria than surface B is supported because it shows that surface B has higher amounts of bacteria than surface A. Let's look at some other examples. This graph right here would tell us that surface A is equal to surface B. As you can see, the blue and the pink are completely even in this graph. What about if surface A was not equal to surface B? It might look something like this. At this point, blue is higher than pink, much higher than pink. At this point, blue is much higher than pink, and then it shifts to pink being much higher than blue. So we can say, yes, surface A and surface B are not equal. What if you look at a graph and it looks something like this? It's a little harder to make inferences on this graph. It's not as clear-cut as the previous graphs I just showed you. For example, at this point, blue is lower than pink. Now all of a sudden, blue is higher than pink, much higher than pink. And then at this point, blue and pink are not that much different. And then now up here, pink is higher than blue, so it's kind of all over the place in this graph. It's not as clear cut. So what can we do to see, are these surfaces even? Are they not equal? Is blue greater than pink, or is pink greater than blue? In this case, we can introduce a new concept that was introduced in your chapter. We used to do the worksheet on page 33 for this part of the lab. However, you will not do that worksheet. I just want to talk about a few different terms. Your lab manual introduces the concept of a null hypothesis. The null hypothesis always sets two groups equal to one another. So for example, using your surfaces, our null hypothesis would say surface A is equal to surface B. We also have a term called an alternate hypothesis. An alternate hypothesis might look something like this. Surface A is not equal to surface B. Now, how can we test whether surface A is equal to surface B? How can we test if surface A is not equal to surface B? Are those groups the same, or are those groups different? We can use computer software to start to tease out this information. This software will give us what is called a test statistics. In this case, we're referring to a p-value. A p-value is what this software program would give you. If the p-value number that the software gives you is less than 0.05, then we reject the null hypothesis. And remember, our null hypothesis is A is equal to B. So we would reject the null hypothesis in favor of the alternate hypothesis that A is not equal to B. What if the software gives us a p-value that is greater than 0.05? We would then fail to reject the null hypothesis that A is equal to B. Now that term, fail to reject, is kind of tricky. Why don't we just accept the null hypothesis? We never accept the null hypothesis, we just fail to reject the null hypothesis. Right? It kind of sounds like the same thing, doesn't it? However, the null hypothesis is referring to an entire population, right? So if we are failing to reject the null hypothesis, we are saying that it is most likely to be true. Now, what do I mean you didn't sample the entire population? For example, when you swab surface A and surface B, do you think that you got all of the bacteria off of that surface? No, you didn't. You just got a sample of the population of the surface you swabbed. Since we did not get every single bacteria off of that surface, we cannot say 100% that the null hypothesis is true, right? It's just most likely to be true. Another example is if a study comes out and says that men are taller than women. Do you think that they sampled every man and every woman on Earth? No. They just took a sample of the population and said that was representative of the entire population. Again, it's just a representation of the population, not the entire population. A couple of announcements before I end this video. You must turn in your worksheet on page 31 next week when you come to take your practical exam. You must use the colony frequencies that I gave you in this video, and I will also provide you a copy in Blackboard. Don't forget to label your histogram. Make sure that you label your X and Y axis. The take-home message from this lab should be 1. Be able to create and make inferences on a histogram. So not only do you need to be able to create these graphs, you need to be able to tell me, what do those graphs say? What can you see? Is there a pattern in that graph? Secondly, you need to be able to use a dichotomous key to identify bacterial species by using colonial characteristics. And lastly, you need to be able to identify bacterial shapes and grouping on a bacterial slide looking through a microscope. I covered these in a previous video. If you have any questions, make sure that you contact your lab instructor before your practical exam next week. Don't forget about the lab practical review this Friday from 10 a.m. to 2 p.m. It is really important that if you missed a particular lab, that you come to this practical review and see what you missed. Please come with questions for the instructors. If you have any other questions, feel free to contact your instructor by email.